Actually, this is a demonstrative learning. So in this lab, we have designed an antenna. Actually, we are not start with the antennas, but we have different type of antennas. We have been designing for biomedical applications. That is for basically you can say that this antenna can be utilized for remote healthcare monitoring. That is the main purpose. So whenever you go for this biomedical application, the antennas can be wearable or it can be placed anywhere in the body. So this is the antenna what we have designed, and this is basically a monopole antenna. Monopole antenna, you will have the length of the antenna to be lambda by 4. So this antenna is being designed for ISM band, which is 2.4 gigahertz. And this band is being chosen because it is industrial scientific, ISM, industry, scientific and medical applications. So normally this can be placed in the body, anywhere, even you can just place it on the hands or whatever it is. Okay, and this is being utilized to send data to the remote hospital so that you can get medical assistance based on that. So normally whenever you place the antenna, it should be flexible. That is, whenever you have a body movements or something, it should be adapted to that. So the material whatever we are choosing should also be flexible, and you can say it is bendable also. So you can just see. So this is the basic antenna we are designed, and it has got a radiating element at the top. Okay, this meandered, half meandered, so modified from this novel antenna, and at the back side you have the ground plane. This is the ground plane. Now this antenna is designed at 2.4 gigahertz, and the material whatever you are using at the substrate is PDMS. That is, you can say it is a flexible and hydrophobic. Hydrophobic, it is like that water lily leaf. Water will not be absorbed on this. Okay, so if the water is being spread on this, it will just move. So it is water resistant, at the same time flexible. Now this has been designed. We'll just see how it is being designed here. You can just see we are using an HFSS simulator. Already people are aware of the simulator. You have attended the workshop. HFSS workshop we are attended. The same software we are using, which is in our lab, and that is being used to design this antenna. And you can just see the basic parameters of the antenna. Whatever you want to check is that return loss, VSWR, radiation pattern. Return loss, you know, that is how much amount of the signal is returning back to the feed. Okay, it should be very less. Okay, only then maximum of the signal will be radiated. Okay, this is the feed what we are connecting. So you can use a coaxial cable or any other cable for feeding the signal here. That is being connected using this connector. So positive of the connector is being placed at the radiating element, and the negative is being connected to the ground. Okay, so this antenna is basically monopole, which has got an omnidirectional pattern. Omnidirectional now, radiation is in all the directions. Okay, you would have seen the downward. So it will be like that. So when you say about radiation, it is like it is all over the sphere. You can just imagine a ball. It is radiating in all the directions. So this is a monopole. So the signal will be radiated around this fully. So if you just see the radiation pattern, 3D pattern, you can just see how it is. See, this is the radiation pattern. So you will have your E plane as well as H plane. That is x, r, theta, pi direction. So in one plane, it will be like, you can just see that you cut it in this, it will be a omnidirectional pattern. Fully signal maximum. This red is the maximum signal. So you will have a maximum around it will be like a 2D pattern. If you just see, you can just see this. This is the 2D pattern. So this graph you can just see. This is the omni pattern. Okay, that is the 3D and this is the 2D image of this. And when you see about the other plane, you just cut it like this to show a figure of 8. 8, how the 8 looks like. That is just cutting in this axis. Okay, then just remember the downnet. Downnet you can place either cut it in the horizontal direction or in the vertical direction. Horizontal direction you will have that omni, one single circle like. And if you cut it in the vertical plane, you will have half one portion of that. So same thing here. If you just cut it here, you will have a pattern like this. That is AP plane and this is the H plane. So if you are just seeing that, I can just see this pattern. Okay. is the pattern here. Okay. Now this antenna has got a lower gain, and very important parameter you have to check is specific absorption rate. Have you heard of it? Specific absorption rate. That is the amount of RF energy which is being absorbed by the body. And by FCC standard, it should be less than 1.6 watts per kilogram for 1 gram of tissue. Normally, when you buy the mobile phone, you should always check that. The mobile phone, it should have some radiations, like it can go for cancerous tissues and all those. So, in order to avoid that, there is a standard limit for the radiation that can be absorbed by the body. Okay, that is maximum by 1.6 watts per kg per 1 gram of tissue. Otherwise, it will be equal to 2 watts per kg per 10 gram of tissues. Okay, so this should be tested for that. That is, we can also check that. You can see we have been tested for that, and we have simulated and tested its SAR radiations by placing this under here 2 mm, 5 mm and 10 mm distance. So when we checked it, it is above 1.6. Okay, so what we have done is we have to improve the performance. So we have made a metamaterial. Metamaterial is one material which is not practically existing. Any material, whatever you are placing, it is not existing in nature with a metamaterial character. Metamaterial in the sense you will have negative epsilon and mu. The characteristics mainly is negative epsilon and mu. Permittivity, permeability, that is, it should be normally positive in most of the cases. Practically there is no such material, but we are developing some material which can perform minus mu and epsilon. This is one which is being developed, and this metamaterial, when you are placing below the antenna, what it helps is the radiation, full radiation whatever you have been giving in the omni side. This, when it is being placed here at certain distance, okay, this will reflect back. It is also metallic structures, no? So because of this reason, this is also designed to the same frequency. So at one frequency, the same frequency, the signal will be radiating back, reflecting from the surface. So what will happen? The main advantage is when you place like this, you can say the signal radiated back. Okay, the signal radiated back, it will get reflected here, and it will also add up when both are same phase. When both the signals are same phase, it can add up with the signal of the actual radiator. So it will become as an additive interface. So the total gain of this antenna will also be improved. Okay, the actual antenna, if it is less, then because of this negative reflecting back of the signal, both is adding up. So it will become as a higher gain. So this will have a advantage that it has been improving its radiation. At the same time, the whatever you increase, that can be lowered because of this reflection. Because there is no radiation back towards the body. We can just place this along with this mix. You can say it will not absorb much of it. So we are reducing the SAR. At the same time, we can also increase the gain of the antenna. Okay, you can just see that how it has been done in this. So this is the basic rectangle. So for each of this, we have made optimization. So what is this length, what is this length, all these parameters, specific parameters we are optimized it, and this is the graph which optimized for these. You can just see this variations. For different values we optimized it. And this is the radiation pattern what I said is being plotted here. And this is the gain. So here it is 1.24 which is a peak gain, and then at 2.4 the design frequency it is 1 dBA. Okay, dBi indicates that it is been with reference to the standard omnidirectional pattern or isotropic, you can say. Okay. Now, when you are placing this antenna with this we have to optimize it separately for the negative epsilon and mu, and I have just checked for different varieties of the combinations like 1:1, 2. The rows and columns it has been improved, and for a maximum 3x3 array you are getting a better performance. So you can just see the pattern, see how it is being changed. See the back radiation when it was completely full in the back, but now it has been reduced at the back side. Okay, and the height should be perfectly like lambda by 2 or something such that it gives the exact phase from both the signals. Okay, so the Previously it was 1.69 for 10 mm and 50 mm, and it is being very close, it is 6.3 mm. 6.3 parts per kg. Now, with the help of this metamaterial, it has been improved to reduce less than 1.3. You can just see, even for keeping the 2 mm distance, it is only 0.52. For 5 mm, it is 0.45, and for 10 mm, it is very less, it is 0.2 watts per kg. So, it's very much reduced. Okay, this is the concept here. You can improve the gain at the same time reducing the SAR performance. Now you can just see how the fabrication and testing already. And this is the network analyzer. You can just test it using this. Already tested results is here. And this is another very important concept that radiation performance is measured in the place of a zero zone. Okay, there should not be any absorptions, no reflections in that. So everything should be absorbed. So such is this called as anechoic chamber. Okay, this we are tested outsourcing. So within this room only we should test the antenna radiation pattern. The pattern indicates what is your electric field, what is your magnetic field, which is being graphically distributed. That only we are seeing as a radiation pattern, that omni pattern what we are seeing now, the same. Now we can just see what is the results of your measured and simulated gain. So you can just see this. It has been improved with metamaterial and without metamaterial. So the gain also you can just see, this is the simulated one with metamaterial and this is the simulated one without metamaterial. There is a huge difference between these both in the gain. So around 5 dB improvement. You can just see it is 4 point. So and this it is only 1.8. So 3 dB improvement you are getting in the gain. Okay. And again the radiation pattern similar one. So this is a basic antenna which has been designed for 2.4 GHz, suitable for biomedical applications, so remote healthcare monitor. Okay.